Okay.
Bismillah ar-Rahman ar-Rahim. We stopped yesterday at the mixing point and we obtained the outlet from the mixer. Now we want to feed those reactants into a reactor, but before feeding them to the reactor we need to heat them up to the temperature of the reaction, and the temperature of the reaction is supposed to be 1200 degrees Fahrenheit. So we need to heat up the outlet stream from the mixer, which happens to be 73 degrees Fahrenheit, to 1200 degrees Fahrenheit. How do we achieve this? We can achieve this in many ways in HYSYS. I can use a heater. What is a heater in HYSYS? It's a heat exchanger, but without knowing the utility side. It just calculates the heat duty of this exchange process, heat transfer process. Or I can use a heat exchanger in HYSYS, for which we have the utility side has to be known and the process side has to be known. Process side is the inlet temperatures and pressures of the feed streams for the process, which are 73 and 1200 degrees Fahrenheit. The utility side, it can be heated using different methods, whether high pressure steam or fired heaters. Instead of using a heat exchanger, we can use a fired heater. In a fired heater, we know the process side and we know that there is combustion process on the other side of that stream. Without complicating things, I'm going to use a very simple heater. And I'm going to place this heater here. Now notice once again, HYSYS did what? It gave a letter starting with E, because it's an exchanger, -100, 3 digits for the number requirement, and the heater symbol, it is reddish and blackish, which means what? It's not connected well, and there is no information on this unit operation. What I need to do is double click on the heater to arrive at the design tab for that heater, and notice it tells me what is the inlet of that heater. The inlet of the heater is stream 3, which is the outlet from the mixer. Okay, and the outlet I'm going to call it 4. And now notice the special thing about the heater, we have an energy stream. Energy stream, why? Because it has to supply the energy to raise the temperature from 73 degrees Fahrenheit to 1200 degrees Fahrenheit. My way of doing this is to attach a Q to the name of the unit operation that I have. If we have an energy stream that is a heat transfer, I will add a Q. If we have a work transfer, such as a pump or compressor, I will add a W. It's consistent with your thermodynamics. In thermodynamics, we usually refer to heat transfer as Q, and we refer to work as W. So notice now what happens. If I add, and let me focus this, those things, now the unit operation, the heater is yellowish, the outline is yellow with green inside, color inside, which means what? This unit operation is connected correctly, but there is not enough information to calculate this unit operation for HYSYS. What do we need to supply for a heat exchanger or a heater? Let us click and look at the traffic sign for HYSYS and follow the traffic sign. What does it tell us? Unknown delta P. What is delta P? Delta P is the pressure drop across the heater, which means what? The difference between the outlet or discharge pressure of the outlet stream and the discharge inlet stream. Where can we find how to specify delta P? We can go now to something we call parameters in a heater or heat exchanger. In parameters, notice what are the options that we have: delta P and duty. Because the reaction is taken at high temperature and pressure, I'm going to set a little bit high delta P, which is 70 psi. And now notice the traffic sign for HYSYS, it tells me unknown duty. What is unknown duty? It tells me how much heat do you want to add to those streams to arrive at 1200 degrees Fahrenheit. I don't know the duty, but what I know is the temperature. Those two specifications are equivalent. Either I specify the temperature, HYSYS will calculate the duty, or I will provide the duty and HYSYS will directly calculate the outlet temperature for me. The easier part is to go and specify for stream 4 the outlet temperature as 1200 degrees Fahrenheit. And notice now what happens. The traffic sign is green once again, which means what? The unit operation is calculated. And now if we look at the color of that unit operation, the color is gray with black outline, which means this unit operation is calculated completely. No need to adjust anything in it. So if we double click on the heat exchanger now, or the heater, and go to the worksheet, we can look at stream 4 and see that the outlet pressure is 499. Why is it 499? We specify delta P to be 70. 569 at the inlet minus 70 is 499. We specify the outlet temperature. Notice now the heat flow in QE. In QE, HYSYS will provide you with the amount of heat required or heat duty of this heat exchanger. I can either look at it from the worksheet, or I can just hover the mouse around that stream, and if you notice, it will give me the heat flow in BTU per hour or the power in horsepower. Almost 8,000 horsepower are required to achieve raising the temperature of this stream from 73 degrees Fahrenheit to 1200 degrees Fahrenheit. So I hope this is clear for you now. Now our feed stream, if we look at it, we can see that the vapor fraction is 1, which means what? The vapor fraction is unity, meaning that we have pure vapor. We don't have any liquid in this stream. While in the feed conditions before the heater, we have almost 50% as liquid and 50% as vapor. So this heater achieved what? It heated the stream and vaporized whatever liquid was there in that stream. Now I need to add the reactor. Before we can add reactors, in fact I can add it directly, and I'm going to use an equilibrium reactor. What is an equilibrium reactor? It is a reactor that is based on calculating the equilibrium conversion based on equilibrium constants. It's exactly like your basic chemistry or 2O2 calculations. But before proceeding, for any type of reactor in HYSYS, we need to have a reaction set, except for Gibbs reactors. So I need to add a reaction set. And because reaction sets are not a part of the simulation, they are part of the basis environment, I need to go back to the basis environment and once again save your work. How do we go back to basis environment? The Erlenmeyer flask. We can look now at the tab that says reactions. If I click on reactions, notice now in the reaction box I don't have any reactions available. All I need to do is do what? Add a reaction. HYSYS has so many types of reactions, whether in the older versions or the newer versions, has more reaction types than just those 5 that are available: conversion, equilibrium, heterogeneous catalytic, or kinetic, or cinder rate. If I want to carry out equilibrium conversion calculations, all I need to do is to specify that I have an equilibrium reactor. So I will need to add that reaction. And notice now, what do I have to fill in? We have to fill in the stoichiometry of the reaction. Any reaction can be written as reactants goes to products. And the convention is reactants has negative stoichiometric coefficients, while products have positive stoichiometric coefficients. I need to add those two reactions. Toluene plus hydrogen, toluene plus hydrogen will yield benzene, which is the desired product, plus CH4, methane, which is a byproduct. Now, unfortunately, some part of the benzene is going to dimerize and form biphenyl and some hydrogen. So I need to add those two reactions. How to add those two reactions? I will go back. Remember, 1 mole toluene plus 1 mole hydrogen will provide 1 mole benzene in the first reaction and 1 mole methane. So all I need to do is select the component here. My convention, there is no standard convention. My convention is to start with the reactants, then products. It's up to you. So I have toluene, I have hydrogen, and I have benzene, and I have methane. Those are the reactants and products of this reaction. So, toluene is a reactant with the stoichiometric coefficient in the equation of 1. Now, stoichiometric coefficient has to be entered in HISES as -1. Negative indicates that this is a reactant, not a product. So, I will enter -1. Hydrogen is a reactant also, so it's -1 also. While benzene and methane are products, they are +1 and +1. Notice, if your equation is correct, your balance error here should be 0. HISES will never give you this ready traffic sign unless your equation is balanced. If it's not balanced, it's not going to work in general. The equilibrium reaction is based on log K equilibrium equal delta G over RT. This is the basic thermodynamics. I can add reaction 1 and I need to add the other reaction. Add another reaction. It's still again an equilibrium reaction. Now, what is our reaction? Once again, I will go here. We have 2 moles of benzene will form 1 mole of biphenyl and 1 mole of hydrogen. So how do I enter such a reaction? I will pick benzene. I will pick biphenyl and I will pick hydrogen. The stoichiometric coefficient for benzene now is -2 because we have 2 moles, and for hydrogen and biphenyl are 1. Notice, if I deleted this, the reaction balance suggests that I have 1 hydrogen. Here it's -2009. And the name of the reaction, I will call it biphenyl reaction, for example. Notice now, we have biphenyl reaction. Reaction 1, I can call it once again benzene formation reaction. You can call it whatever kind of name that makes meaning for you. Now, before we return back to the simulation environment, one final step is to add the reaction set to the fluid package. What is the fluid package we have used is Fink-Robinson. We need to add that reaction set to the fluid package. Why is that? Notice that log K is delta G over RT, we need delta G. How do we calculate delta G? It's H minus Ts. How do we calculate H and S from the equation of state? So we need to tell HYSYS how to calculate those properties by attaching those reactions and their properties to the proper fluid package. So all I need to do is to add to fluid package. HYSYS now asks me the fluid package is basis 1, number of component 5, and it's being Robinson. All I need to do is add set to fluid package. Now notice associate fluid packages is basis 1. Now we are done. So we can return back to the simulation environment. Now we can return back to the reactor and make proper connections. What is the inlet of this reactor? It's the outlet from the heater, which is 4. By default, HYSYS assumes equilibrium reactors to be a two-phase reactors. They have both vapor and liquid. Don't worry. Give him two streams at the outlet, vapor and liquid streams. Our reaction is going to take place in the vapor. How can you check this? Just check the outlet liquid flow rate. It's going to be 0. So don't worry. I will call those 5 and 6. So notice once again, let me just reconnect, zoom this one. Notice now in HYSYS we have something that HYSYS calls energy, and it's an optional stream. We can heat up the reaction contents. We can cool down the reaction contents to any desired temperature that we would like to have. If we do not add this energy stream, HYSYS by default assumes the reaction to take place at adiabatic conditions, which means what? Q equals 0. I'm going to leave the reactor as adiabatic reactor, so I don't need the energy stream. But if I want to carry out isothermal operation, all I need to do is add an energy stream, and according to our method, I will add a Q next to the name of the unit operation. So the energy stream will be QERV-100. But right now, we don't need this. All we need to do is attach the material streams. Notice now we have a tab here in the reactor. In the tab section, for the reactor to operate and HYSYS to calculate it, we need to define the reaction set. And notice only one reaction set is available, which is global reaction set. Once I picked this reaction set, notice what happened. The traffic sign became green. HYSYS calculated everything for us. And we can look at, instead of the details, and we can go to the results and look at some data based on the equilibrium calculations. HYSYS estimates that the actual percent conversion of benzene formation reaction, which is the conversion of toluene, by the way, it's not for benzene, benzene is a product, it's 97.13. Toluene, the equilibrium constant for the base compound for the first reaction is 100. And the reaction extent, the Xi, as in the standard notation, it's 266. While for the second reaction, the base component, which is the reactant, it's benzene, and its equilibrium constant is 0.1. So evidently, the first reaction is the main reaction, the second reaction is a secondary reaction based on the equilibrium constant values. And we can look at the worksheet, and just to make sure that we have only one phase reaction. Notice the mole or the mass flow rate for the liquid phase, which is stream 6, it is 0. So HYSYS really operated in the vapor phase. We can look at the composition now. And if you notice, in stream 4, which is the feed stream, we have almost stoichiometric ratio between toluene and hydrogen 50%, 49.8%, while at the outlet stream, stream 5, we have almost 31% benzene and 0.01% toluene, only 0.10% hydrogen, 48% methane, and 10% of biphenyl. So evidently a reaction was calculated in this case. So what did we learn up to now? We learned how to operate a mixer, a heater, and an equilibrium reactor, and how to add reactions and reaction set. We'll stop now and we will continue with extra 2-unit operations in the next lecture, which are the component splitter and the distillation unit. Thank you.